Hello everyone, and welcome to today's Chem lesson. Today we're going to begin our fourth unit by looking at the idea of an atom and how that idea has changed over time. How did we go from the picture of the atom that the ancient Greeks made thousands of years ago to the model of the atom that we know is true and we've witnessed under a microscope today? Right, the first thing we're going to talk about is the actual ancient Greek model. Right, the ancient Greeks were the first to philosophize and think about what an atom might look like or what an atom might be. Right, they thought that everything was made of these atoms, or if you took them and broke them down over and over again, you would end up with something so small that you can't break it apart anymore. And this is their idea of the atom. It was just a sphere, right? It was just a solid sphere. And they were like, this thing is an atom. And this idea stuck, right? It's not a bad idea. It's not that far from the truth. And so it stuck around, and people referred to the atom for years and years and years. And it was actually until around the late 1800s where somebody else came along and thought about the atom and did some experiments and tried to actually quantify and get a picture of what an atom looks like. The first scientist, the first modern scientist to look at the atom was a guy named Dalton, and he came up with the atomic theory. But before we talk about the atomic theory, we want to talk about the idea of law of conservation of mass. Something that's important to talk about as we move forward in this unit is the idea that mass is never gained or lost, right? Mass can only be changed from one form to another. Right? So when we talk about, I burned this piece of wood and I ended up with smoke, the weight of that smoke and the weight of those gases that you made by burning that piece of wood should weigh the exact same as your piece of wood. Right? Mass is not created or destroyed during chemical reactions. The only time mass is created or destroyed is during a nuclear reaction, but those are not ordinary. And so when we look at the mole and chemical equations later in this unit, we're going to come back to this idea. When we talk about balancing equations, we're going to look at this idea. And as we talk about the atom, we're going to look at this idea. But after the ancient Greeks came up with this idea of an atom is a teeny tiny sphere of something, Dalton came along and makes the atomic theory. And the atomic theory summarizes the experiments of a bunch of other scientists into these 5 statements. And he doesn't actually change the look of what an atom is, right? The ancient Greeks say it's a small sphere, and Dalton actually doesn't change that, right? Dalton says, okay, it's a small sphere. But what Dalton does do, right, and what these other scientists do that he's summarizing their work, what he does with this is give us a list of rules to look at while we're looking at and studying the atom. All matter is composed of extremely small particles called atoms. Atoms of an element are the same. Atoms of different elements are different, right? So if I have a gold atom and another gold atom, those should be exactly the same. If I have a gold atom and an oxygen atom, those should be different. Atoms cannot be subdivided, created, or destroyed. Right? This one's a little iffy, but at the time, no one could prove it otherwise. Compounds of different elements combine in whole number ratios. Right? That means when you look at carbon dioxide, it's always CO2. It's never C.60 1.2. Right? Even though that's the same ratio, right? It's a 1 to 2 ratio. You can't have this version of carbon dioxide because it's not whole numbers. Right? There's no such thing as 0.6 of an atom, right? An atom is an atom. You either have 1, 2, 3, 4, or you can't really have pieces of an atom. And then lastly, in chemical reactions, atoms are combined, separated, or rearranged. Right? We're never turning oxygen into hydrogen. Right? We're taking things that are separate and recombining them as if they were something like Legos to make a new combination of stuff. And we're taking 2 H's and 1 O2 to make 2 copies of H2O. Right? Rearranging our atoms to make something new. Taking apart our molecules to get elements back. And the atomic theory is great. Right? The atomic theory says a lot of really important things. A lot of things that hold pretty true. Right? They're not all true. Right? We know that atoms are made up of protons, neutrons, and electrons. We know that they can be created in a lab. We know that they can be destroyed with nuclear chemistry. But in the 1800s, nobody knew this. Right? But almost all the rest of these are true. And this, the second one, needs just a small adjustment to be true. But it's nearly true. And so for 1800s, this is a great set of rules to look at. And over the next couple of years, as science advanced and we got more and more tools and better tools to look at atoms with, we learned more and more. J Thompson was the first one to evolve the physical look of the atom beyond this idea of a sphere. Right? The ancient Greeks and Dalton thought the atom is this sphere. Thomson was doing experiments with a cathode ray tube, which is a really thin glass tube which you run a current through. Right? You run electricity through one end to get to the other end. And in this tube there are very, very few gas particles. It's almost a vacuum. Right? It's almost totally empty, but there's a couple of gas particles in there. And as he was doing his experiments here, he noticed, when you run a current through, and this is what a cathode ray tube does, when you run a current through, you get a beam of light. And I wish we were in person so I could show you what this looks like. But you get a beam of light through the cathode ray tube. Essentially, this is a neon sign. Right? Old neon signs were cathode ray tubes. Right? You run electricity to excite the gas in there, and by exciting the gas, it changes color, it gives you this light. But what was really interesting is that while he was doing his experiments, he put a magnet near the cathode ray tube, and that bent the beam of light. Instead of going straight across, the beam of light now bent towards the magnet. And Thompson looks at this and he says, that's weird. This shouldn't be happening. There's got to be something in here that is attracted, excuse me, to this magnet. There's got to be something in here that's affected by this magnet. And so Thompson makes the plum pudding model of the atom, which says there is a big positive atom, and nestled within this atom, right, kind of buried in this atom, are little negative chunks, right, like the plums in plum pudding. Right. So the atom itself is this big positive thing, and there's all these little negative things that get excited by electricity, which he calls electrons. All right, they get activated by the electricity and they turn negative, and that's what gives them this attraction to the magnet. And he's not right, but he's also not wrong. Right? There are electrons in the atom. This just isn't what the atom looks like. But by looking at a cathode ray tube and not a microscope, right, not having the equipment he needed to actually take a look at this, this is the best that he could come up with. And it's closer than here's just a dense sphere. Right? His model of the atom is closer to the truth than the previous one. And that's what matters. He publishes his work, he does all of his experiments again, he records all his data, and this is his model of the atom. And that sticks for a little while until someone else comes along and does an experiment. The next person to do an experiment is a guy named Rutherford. Rutherford wants to prove Thompson correct. He wants to prove that the plum pudding model is the model of the atom, and that it is totally correct. And so he sets up an experiment to try to prove this theory correct. He does what we call the gold foil experiment. And basically what he does is he has a lead box with a hole in it, and this lead box shoots out teeny tiny particles. And he shoots it at a piece of gold foil. And he says, I am shooting ping pong balls at a brick wall. Alright, that's the analogy here. Right, he's got these teeny tiny particles at this gold foil that's as thin as he can get it. He says, I'm shooting ping pong balls at a brick wall, and I want to see what happens to them, right? If Thompson is correct, these should all just bounce off. And I should see them develop this photo paper that I've put around. Right? He puts around photo film, which will catch any of these alpha particles and develop at the spot where they land. And he does his experiment. And he expects all of these particles to bounce off and land here on the outskirts, right? Deflected, as you would expect, shooting ping pong balls at a brick wall. But instead, what he sees is almost all of the particles go through the gold foil. And only a couple of them, and only a small percentage, bounce where he expected them to. And he's confused by this. He looks at this experiment and these results and he goes, what? I just shot ping pong balls at a brick wall. And they went through the brick wall. That shouldn't have happened. And so he gets to thinking and he says, well, maybe this isn't a brick wall. Maybe it's not a dense sphere. There must be a bunch of empty space. Rutherford takes this experimentation and comes up with a new model of the atom, saying that an atom is mostly empty space, except for a small, dense nucleus in the middle of the atom. So he set out to prove Thomson right, but in fact proved Thomson wrong. Right, he says all of this is empty space, and there's a small, dense nucleus in the atom. Right, that's why so many of those particles passed right through the gold foil. Right, they were going into all this empty space. But a couple of them bounced back because they collided with the nucleus and bounced away. And so that's even closer to the correct model of the atom. It's even closer to what an atom actually looks like. But he didn't know where anything went. He doesn't know where the electrons are, where the protons are, where the neutrons are. He doesn't even know whether protons or neutrons are a thing yet. And then we get to the model that we're going to use in class. We are going to get to Bohr's model of the atom. Right, and Bohr is important for a couple of reasons, right? Not only did Bohr discover a new model of the atom, or theorize a new model of the atom, he also discovered the idea of the excited versus ground state, which is something we're going to talk about later in this unit. Right? But his experiment, which we will talk about in more detail later on, really came down to discovering the fact that electrons can only exist at certain places in the atom. Right? There are certain distances from the nucleus where electrons can exist. Electrons can only exist on these dotted lines, which exist at very specific distances away from the nucleus. Now, his experiment itself was pretty complicated, but he was testing energy inputs, right? He was basically shocking the atom and observing exactly what happened as he used different amounts of electricity to shock the atom. And he discovered that even with variable amounts of energy, he got the same set of results every time, which then led to this model of the atom. Essentially saying when the atoms or electrons get into the atom, they pick a seat like in a classroom. Right? They sit in the first row, they sit in the second row, they sit in the third row, they sit in the fourth row. But nobody sits on the floor in between the rows. Nobody sits behind two desks or in between two desks without being at one of the desks. Right? There's seats and the electrons take those seats. They can't just go wherever. They can't just sit on the floor or sit over here or over here or over here. They have to pick a desk and sit at it. And that model of the atom, right, this one, Bohr's model, is the one we're going to use in class, the shell model of the atom. It's also the model you're probably most familiar with seeing, right? When you see Jimmy Neutron or Big Bang Theory and they show an atom or with, the electrons kind of circling around it like this, that's Bohr's model of the atom. Right? Looking at these different rings and how they have electrons on them. But it's not the most advanced model of the atom. It's not the best model of the atom. The most advanced, the current model of the atom, actually looks nothing like that. It's the quantum mechanical model, and it takes the models of the atom that we have looked at so far, and it gives us our final picture. Put Rutherford's back up here. Let's put Bohr's model back up here. The quantum mechanical model was found by actually looking at atoms under an electron microscope. And it's close to Bohr's model, but it makes one specific change. Right? Bohr's model talks about electrons like they're planets orbiting the sun. Right? They follow this pattern, this circular pattern, and you can say, here's my nucleus in the middle, there's 2 electrons circling, there's 3 electrons over here, circling. But it's not actually like that. When they got into the electron microscopes and they actually looked at the atom, they found that electrons don't behave that way. Yes, they exist at specific distances, but really what it is instead of a orbit like a planet, it's a cloud of probability, which is a much more difficult concept to grasp. Imagine we're back in school and the dean is looking for you. Right? You dropped your ID card, or you dropped a book on the floor and they found your name in it and they're trying to give it back to you. They know your schedule, so they know, they have a pretty good idea of where you are. But if the dean comes to your 4th period class and knocks on the door and opens it up, there's not a 100% chance that you'll be there. Right? You could be in the bathroom. You could be going to get a drink of water. Right? They know where you are going to be most of the time, right? They have a 95% chance of getting it right, but there is the chance that they're wrong. And that's the idea of this probability, right? Bohr's model can pin down. Bohr's model is like the dean coming into the room and knowing exactly what seat you are taking up. Right? They know exactly what room, exactly what seat, exactly what row you're sitting in the classroom without ever having seen it before. But the quantum mechanical model takes this idea of the electron cloud, right? The idea of the probability of where the electron is, and defines that, right? They can come looking for you in your 4th period class, but you might not be there, right? They don't know what seat you're sitting in or what row you're sitting in. They only know that you're somewhere, or you should be somewhere, in this specific room. And confusingly enough, these clouds of probabilities are called orbitals. Most probable location of an electron. Right, the quantum mechanical model introduces this idea of the orbital, right, a cloud of possibility. It's not always guaranteed that the electron will be where you expect it to be. But there's a 95% chance it will be there, or 96% chance it will be there. And because of how much more confusing the quantum mechanical model is, we actually stick to Bohr's model, even though we know the quantum mechanical model exists. The difference in Bohr's model and the quantum mechanical model for the stuff we are going to look at over the next couple of months, over the rest of our videos, is slight. Right? We can say that the shell model, the Bohr's model, is correct and operate off of that without making a lot of assumptions. There are going to be times where we look at something and say, well, because we're not using the most advanced model of the atom, this doesn't follow the rules. Right? Or this operates differently than what Bohr thought, because we now know that the quantum mechanical model exists. But if you ever go on to more advanced chemistry, if you ever go on to AP or college level chem, you'll learn about the orbitals, you'll learn about the suborbitals, the shells, and how they, overlap and combine and mix and hybridize and all that fun stuff. But for us, we're sticking with our planetary model, our shell model, and we're using that as we continue onward. And I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance, and I will see you there.